Okay folks, so today what we have to do is we have another surface development question, and this time it's on a transition piece. So we'll just read the question and see what it's asking us to do. So for question 1 it says, the graphic shows a sheet metal transition piece. The projections of the transition piece are shown, or they're given. Complete a one-piece surface development of the transition piece and use the given point 1 as the starting point of the development. So we can see point 1 is given to us down here. Now, just going to talk it through here before we get started. We can see obviously we've got a 3D graphic here, and we have the elevation and plan view here. Now if you look at the 3D graphic, obviously there's a top bit here and there's a bottom bit down here. If you look at the elevation and the plan, we can see that we don't have the bottom bit and we don't have the top bit. All they want us to do essentially is the outside. If we break up these, see these bits here, these outside triangular parts. So if we actually take the piece as it is, there's no real base to it and there's no actual top covering on it. If we take it, it's just one sheet wrapped around to make this shape. So the top bit here, there is no actual square bit on top there, and then the bottom bit, the rectangle, there's no actual rectangular bit on bottom there either. It's just the B sheet essentially as in it was cut out and folded back together. Okay, so what we have to do is we need true lengths to be able to complete this. Okay, so looking at it and how many lines we actually have, let's take the bottom part of it first. If you imagine where the base was, we know we have no base actually there, but we have 4 edges on the bottom. And if we take 1 to 2, 2 to 3, 3 to 4, and 4 back to 1, every one of them I know it is a true length. And the reason I know it is actually a true length is because, well, if you take 1, 2, 3 and 4, every one of them, if I was to use labels, 1 and 2 would be in this position here, and 3 and 4 would be in this position here. Now, every one of them is on the ground. So if I take, let's say, the line 2 to 3 here, well look, 2 to 3, it's parallel with the XY line. Therefore, in my plan view, it has to be true length. And in my elevation, it also happens to be a true length. Now, 1 to 2 in this case. Now in my elevation we can see that they're both on the ground, but if you imagine they're like going in this direction in my elevation into the page, but we only see them as a point view in the elevation. That means in plan, at this point, this line here is a true length as well. So we have a true length for 1 and 2, we have a true length for 3 and 4, true length for 1 and 2, 2 and 3, 3 and 4, and 4 and 1. And then it's the exact same with the points here on top. 5 to 6, 6 to 7, 7 to 8, 8 back to 5. Because all of them, if I was to label them in my elevation, well 5, if we followed it up, would be directly up here. 6 and 8 would be in the middle. And then obviously 7 is on the outside. Just to prove that to you, I'll just mark them up there quickly. So, 5 is up here. We can see it matches up. 6 and 8. And then number 7. Okay. Now, every one of them, in elevation, they might not be true lengths, but what we know is they are all parallel with the XY line. Okay? And that is very important, because any line that is parallel with the XY line in one view means it is a true length in the other. So there's our XY line. That means the distance, let's take it 5 to 6 here. That down there is a true length, because look, 5 to 6 here is parallel with the XY line, therefore it's a true length down here. So all these lines here are true lengths. Now, if we take that so far, so every line on the outside of the rectangle, 1, 2, 2, 3, 3, 4, 4 to 1, they're all true lengths. 5, 6, 6, 7, 7, 8, 8, 5 are also all true lengths. Then, the only lines we actually have left are these lines that are connecting all the points in the middle. And as we can see that, if we look at them, look, 1 to 5 is the same as 5 to 2. However, 2 to 6 is not the same as 2 to 5. So what we need to do is we need to figure out the true lengths and then just recognize which ones we're going to be able to use afterwards. So what we do is we treat it like cones, the cones principle that we have previously learnt. So for 5 to 1, which is the same as 5 to 2, 7 to 3 and 7 to 4, I want to figure out the true lengths for 1, 2, 3, 4 of those lines, and then I'm going to figure them out after for these 4. So to be able to do that, if I imagine 5 as my apex of a cone, and 1 is where the cone is going down to the ground. I need to see that as the extreme generator of a cone to get the true length of it. So what I'm going to do is I'm going to rotate it down. So where 5 is, I'm going to come out here and I'm going to rotate from 5 to 1. Okay, where it hits here, if you imagine that was the extreme generator, and imagine now we are looking straight in at it, that's why I see it as the extreme generator. 5 hasn't moved, but 1 has. And the new position of 1 now is out here. That is my new 1, right there. And what I'm going to do is I'm going to join that now to 5. And there we go. What I have found there is the true length of 5 to 1. And that would be a true length for 5 to 1, 5 to 2. And if we take it 7 to 3 and 7 to 4. Just write those in so I know exactly what I'm going to use. There's 7 to 3 and 7 to 4, if that makes sense. Now, if I wanted to find the true length of 6 to 2, which would be the same as 6 to 3, 8 to 4 and 8 to 1, how would I do that? Okay, so let's take 6. Okay, so keep 6 as the apex of a cone. We can keep it in the exact same position. Okay, so that's the apex of a cone. If you imagine a cone, for starting at 6, the center will be there and we'll be revolving it around 6. So at 6, and I'll take it around this side so I keep it nice and neat on my page. So we're taking 6 and 3 in this case now. So at 3, remember, we'll see the extreme generator. At 3, I'm going to literally just rotate it up. Hasn't made too much of a difference, but it's still significant. And where it hits here, I'm going to join that to 6. And it might be hard to see that there, but there's about a mil or two in the difference. Okay, and that there is my true length of the line. True length of the line 6 to 3. Which is the same as 6 to 2, same as 8 to 4, and then the same as 8 to 1. Okay? Now, what we are going to do is we're going to use all those true lengths to get the development of that surface. So in a second now, I'm just going to pan out, and because I need more room for you to see it down here. Okay. Alright. So now at this stage, guys, what we're going to do is we've explained how to get all these true lengths up here, and we've talked through that. With all those true lengths now, we're going to complete the surface development of this problem. So they've given us a start point here of 1, and what we have to do is we just have to essentially complete it out after that. So if I take, it's broken up into a series of, as we can see, triangles, and we're going to use those triangles to complete the whole surface development of it until we get back. So if I take the triangle 1, 2, 5. That's the very first one I'm going to start with, and I've been given 1, and I know the true length from 1 to 2, and I found the true lengths from 1 to 5 and 5 to 2, so I should have no problem drawing that. And if I start at 1, 2, 5, obviously I'm going to finish with the last triangle is going to be joining back onto that at this edge. So if you imagine, we're going to draw this one first, second, third, fourth, fifth, sixth, seventh, back to this one here. So I'm going to finish, if I did 1, 5 as a line, I'm going to finish at 1, 5, because it has to join back up around it. So starting with 1 to 2, I'm going to do a straight line down, and I'm going to take the true length straight from my plan view from 1 to 2. So I've located point 2 there in that position. That is my point 2. And now I'm going to take the true length from 1 to 5, which I found this guy be, or this fellow over here. Because I brought 5 out, rotated it down, or sorry, I brought 1 down and then brought it up, and I got the true length of it from 1 to 5. So 1 to 5, so 5 is somewhere in there, 2 to 5, which is somewhere in there. Now, that's the first triangle got, and I've got the line 2 to 5. Now I need the line from 5 to 6. So, straight away there, I can take the distance from 5 to 6, which is that's a true length, and from 5, I'm going to swing a point, because I have 5 already, so somewhere out there is going to be, along that arc is going to be my 6, and now I just need the true length from 2 to 6, and we discovered the true length from, as I said, it was 6 to 2, you can see it up here, so it's this distance right here. Now it's not to that exact point there, but it was to the further out one just here that I got. That was the true length there. So that's the one I'm always going to use, the one on the outside. It's a bit hard to see on the camera, but if you had followed this method over here where we rotated up and brought it up. So I got that distance there, and I'm going to swing that from 2. And that there is my exact positioning of 6 right there. And once again, join those up. And what we're going to do is we're going to continue on in that sequence until we get all the way back to the start. Very simple. So far I've done this one. Now we're going to do this big one here. So, same thing. At 2, I'll take the true length from 2 to 3. It's going to be somewhere down here. Might actually swing that arc a little bit further, because I'm not sure exactly where it is. I've done 2 to 3, I've got 2 to 6, now I need 6 to 3. So 2 to 3 is somewhere along this arc. I already have the line 2 to 6, which is up here. Now I need the line 6 to 3. So go to the right one, get this true length again. Go on to my 6. And there we go. There's my tree, right there. Okay, same thing, build it up slowly. And we just keep working in that sequence. Okay, next one, 6 to 7. Somewhere along there. Now I need the length from 3 to 7. And in this case, it's this true length. That one. And my tree is down here. Now it's slightly off your screen at the moment, so just make them match up. There's my 7. Okay, I'll just rotate it up there a bit so you can see where I'm getting it from. So there's my 3 to 7. Okay, now I have to do 3 to 4. So I've got 3 down here, 4 is somewhere out there. Now I need 7 to 4, and 7 to 4 is this guy. So I have 7. There's my 4. Okay, now I need, so I've done 5 to 6, 6 to 7, now I'm on 7 to 8. So you can see how we're just building it up and following it around. 7 to 8. So 8 is going to be somewhere along there. Now I need 4 to 8. And my 4 to 8, if I label it properly, it's this guy here. And I do it from the 4. So, as we can also see, labeling is extremely important. So there's my 4 to 8. We're nearly complete at this stage. So, 4 to 8, now I'm 4 to 1. On to the last section of it now, 2 more to do. So, 4. So somewhere along there is going to be my 1. And now I need 8 to 1. And my 8 to 1 is this guy here. So I have 8, find 1 exactly, there's my 1. Join it all up. And the last thing then I need is 8 back to 5. there. And if you remember, we started with 1 and 5, so we have to finish with 1 and 5. 1 to 5 was this true length here on the right. There's my 5. Okay. Now, at this point, it's just a case of having in the detail. So I'm going to fast forward this so you can see it being done. There we go. That is the complete surface development of that transition piece there. It was all just about getting the true lengths and recognizing what true lengths join to what to be able to complete it. You need to have good understanding of how to be able to obtain true lengths on lines that are not parallel with the principal planes. So as we did here with 5 and 1, we use 5, if we imagine that as the apex of a cone, rotated 1 down, brought it up and joined 1 back up to 5. And the exact same thing with 6 and 3. And just recognizing that 6 and 3 was the same as 8 and 4, or 8 and 1. Okay? Question done.